When an object travels into our solar system from the deep spaces between the stars, I always pause before naming it. A comet is supposed to behave in certain familiar ways, but 3I Atlas has not followed that script. It looks like a comet, yet it acts in ways that no comet in our neighborhood has displayed so consistently. So the question that lingers is simple: how do you understand something that wears a familiar shape but carries unfamiliar behavior? I remember looking at its first published orbit the moment the curve revealed that it was not a loop but an open path. An open path means it will never return. It will pass through, once shed what it carries, and then slip back into the darkness between the stars. That single visit nature gives a strange weight to every measurement that follows, because you cannot wait for a second chance. Before we begin, let me leave you with one truth that is both quiet and enormous. Every interstellar visitor is a free sample from another star system shaped by conditions we could never witness direct. When a fast-moving object the size of Manhattan crosses into the inner solar system on a one-time hyperbolic path, the question forms almost automatically: is this simply a natural fragment of ice and dust? Or could it be something designed? 3I Atlas forces that question because it enters the conversation with a profile that is unusual on several fronts. It is interstellar, meaning it does not orbit our sun day. It is large, tremendously volatile, and active in ways that do not match the majority of comets we have studied. And because it comes from outside our system, it carries a sense of unfamiliarity that makes speculation easy. But speculation and evidence are not the same thing, and separating the two is the work we have to do. 3I Atlas is only the third confirmed interstellar object ever observed. That fact alone puts it into rare territory. For most of human history, every comet, every asteroid, and every meteor came from within our own gravitational neighborhood. We built our expectations of comet behavior from objects that were born with our sun objects that formed in the same disk of gas and dust that eventually became Earth. When something arrives from outside that origin, we should expect it to differ. The chemistry may differ, the dust grains may differ, the ices may respond to sunlight in new ways. Unfamiliarity is not a sign of design. It is simply what happens when the sample size expands. Still, the first days after discovery created a predictable ripple. Images showed a brightening object with early activity. Instruments measured large amounts of carbon dioxide and a surprisingly small amount of water. In certain photos, the coma shifted color. Polarization measurements suggested that its dust interacted with sunlight in ways that were not typical of local comets. And as new data arrived, the commentary began, some reasonable, some careless, some deliberately dramatic. It became a story not only about an object in space, but about how the public reacts to uncertainty. The strongest version of the alien craft hypothesis has been voiced by Avi Loeb, a theoretical astrophysicist with a long record of engaging with ideas about potential extraterrestrial technology. He argues that elements of 3I Atlas's brightness pattern might indicate a compact light source, not merely sunlight reflecting off dust. He points to possible non-gravitational acceleration that, in his view, could exceed what outgassing alone would produce. He notes that its path through the inner solar system brings it near several planets, and he estimates that such proximity would be statistically rare if the object had approached randomly. From these points, he builds a scenario in which 3I Atlas could be a reconnaissance craft, perhaps nuclear-powered, perhaps shedding mass in a controlled way, perhaps even releasing smaller probes. These ideas gain traction online, partly because they are presented with confidence and partly because they match a pattern of public fascination. Social platforms favor high-energy interpretations. A strange object becomes a narrative device almost immediately. Its details are compressed into simple phrases: alien engine, mysterious acceleration, possible probe. The complexity disappears, replaced by a headline that suggests finality. Once that transformation happens, it becomes difficult to return to the actual measurements, to the unresolved uncertainties, or to the mundane explanations that scientists typically favor first. The mainstream scientific view differs because it operates under a different discipline. It begins with the principle that unusual behavior in a natural object should be explained by natural processes unless clear evidence suggests otherwise. In the case of 3I Atlas, all current data remain consistent with a comet undergoing vigorous outgassing. That includes the early activity, the large presence of carbon dioxide, the shifts in color produced by changing chemistry, and the slight trajectory deviations that outgassing naturally causes. Even the possible fragmentation can be explained by rapid loss of volatiles and structural weakness near perihelion. These features may be uncommon among local comets, but local comets are not the standard by which interstellar objects should be judged. What makes Chapter 1 important is not choosing a side, but understanding the shape of the question itself. The alien craft hypothesis is appealing not because it fits the data best, but because it supplies a clear narrative where uncertainty exists. It offers an agent, an intention, a purpose. 3I Atlas in that framing is not a chaotic mix of ice and minerals. It is a constructed artifact with a mission. That story is easier to grasp than the idea of a natural object with unfamiliar chemistry and behavior shaped by billions of years of exposure in an environment we cannot reconstruct. But a scientific approach demands a different posture. Instead of filling the gaps, it measures them. Instead of assuming intention, it tests for it. Instead of starting with the most dramatic explanation, it begins with the simplest one that fits the evidence. When an object displays early outgassing, the first question is about chemistry. When a trajectory shifts slightly, the first question is about venting gases. When mass loss appears extreme, the first question is about structural integrity. And when a visitor comes from beyond the solar system, the first question is about what conditions in its home system might produce such features. This chapter is therefore a way of framing the investigation. 3I Atlas is either a comet behaving in unfamiliar ways or a disguised vessel navigating our system for reasons we cannot yet determine. One of those explanations is extraordinary, and extraordinary claims require evidence beyond anomaly and coincidence. The other explanation is still remarkable, but does not require technology or intention. Only the physical behaviors we know comets can display when placed under the conditions 3I Atlas has encountered. The question remains open at this stage because the journey through the data has barely begun. But asking the question correctly is essential. It prevents us from leaping ahead of the evidence and instead keeps us aligned with what the measurements actually show. In the next chapter, we step back from speculation and identify what 3I Atlas truly is. In the simplest terms, its classification, its discovery, its naming, and the path that brought it across the gulf between stars into the narrow window where we could observe it at all. If you and I are going to ask serious questions about 3I Atlas, we need a clear picture of what it is before we argue about what it might be. That starts very simply with how it was found and how it was named. The first time it appeared in our records was on the night of July 1st, 2025, when one of the Atlas survey telescopes in Chile picked up a faint moving point of light against a crowded background of stars near the direction of the galactic center. Atlas, the asteroid terrestrial impact last alert system, is designed to spot objects that might one day cross Earth's path in dangerous ways. On that night, it did what it was built to do. It found something new. It just happened that this particular object was never going to come anywhere near us. At first, it was only a sequence of positions on the sky, a dot that shifted slightly between exposures. From those shifts, astronomers computed an initial orbit and gave it a standard comet designation, C/2025N1 Atlas. The letter C marks it as a non-periodic comet, an object that does not return on a short, predictable schedule. The code N1 tells other astronomers that it was the first such comet reported in the second half of July that year. The tag Atlas credits the survey that made the discovery. By itself, that label does not claim anything exotic. At that stage 3I Atlas was just another distant object with a path that still needed refining. Within days, more telescopes joined in. Observatories in Arizona, Hawaii, Chile, and elsewhere supplied fresh measurements. Some early reports described a star-like point with no obvious coma. Others, taken with longer exposures and better seeing, began to show a very faint fuzz and the hint of a tail. That shift is important. An asteroid is a bare rock. A comet is a nucleus surrounded by gas and dust driven off by sunlight. As soon as the faint coma became clear, the community settled on calling it a comet, and the original C/2025 N1 designation was confirmed. The real surprise came when the orbit solution stabilized. When you track a new object over days and weeks, each new position sharpens the picture of how it moves in 3 dimensions. For most comets, those refinements pull the orbit into some kind of stretched ellipse around the sunday. With this one, the more data came in, the more the computed path refused to close. The eccentricity, which tells you how stretched an orbit has climbed above one and stayed there. That is the threshold between a bound orbit and a flyby. Once the dust settled, the numbers showed a clearly hyperbolic trajectory. In simple terms, 3, I-Atlas was not circling the sun at all. It was dropping in, swinging past once, and heading back out into interstellar space. At that moment, the naming changed. The Minor Planet Center assigned a second label, 3I/Atlas. The number 3 marks it as the 3rd confirmed interstellar object to pass through our system, after 1I Oumuamua in 2017 and 2I Borisov in 2019. The letter I stands for interstellar. The word Atlas again honors the survey that first noticed it. When someone says 3I Atlas, they are using this second name, the one that encodes the fact that it does not belong to our sun at all. Its direction of approach points roughly back toward the constellation Sagittarius, toward the crowded inner Milky Way. That does not mean it came from any specific star there. By the time an object has wandered through the gravitational fields of many stars, its incoming path no longer points neatly back to its birthplace. What matters is that its speed and direction cannot be explained by any known encounter inside our solar system. There is no record of a close pass by Jupiter or Saturn that could have kicked it onto an escape path. Its hyperbolic orbit is best understood as something it already had before it crossed our boundary. The shape of that orbit is interesting for another reason. In 3 dimensions, it is retrograde and tilted only a few degrees relative to the plane in which most of the planets travel. Retrograde means it moves around the sun in the opposite direction to the planets. The small tilt means that if you could see the whole solar system from the side, its path would sit in almost the same flat sheet as the planetary orbits, just running the wrong way. That combination is uncommon but not impossible for a random interstellar visitor. It is one of the details that later fed speculation, but on its own, it does not imply intention. In terms of timing, the key dates are straightforward. 3I Atlas passed closest to Mars in early October 2025 at a distance of a few tens of millions of kilometers, close in astronomical terms but entirely safe. Its closest approach to the Sun, the point we call perihelion, came in late October, around October 29th, at a distance of about 1 1/3 astronomical unit. That places it between the orbits of Earth and Mars, but not especially close to the Sun, compared to many comets that dive much deeper. After that, it began to climb back outward, crossing the plane of Earth's orbit and reaching its minimum distance from our planet in mid-December, roughly 1.8 astronomical units away. That is nearly twice Earth's distance from the Sun and far beyond any realistic threat. From your point of view as an observer on Earth, all of this reduces to a simple fact. This object is a one-time event. It was discovered when it was still far from the Sun, moving inward. It will swing through the inner solar system over the span of months, then recede into darkness, and we will never see it again. There is no second pass to check our work, no long, slow, repeatable orbit to study at leisure. Every image, every spectrum, every radio detection must be taken within this single window. For astronomers, that has 2 consequences. The first is practical. Observing time on large telescopes and space instruments is scarce, so a rare interstellar visitor must compete with all the other targets in the sky. Proposals have to be written, schedules adjusted, instruments tuned. The second consequence is psychological. Knowing that 3I Atlas is an interstellar traveler and knowing that it will not return sharpens the sense that any unanswered question about it may stay unanswered for a very long time. That pressure can make some people more willing to speculate and others more cautious. For our purposes, what matters in this chapter is that 3I Atlas is now firmly classified as an interstellar comet, discovered by a survey built to guard Earth flagged, first as a potential near-Earth object, then reclassified as a harmless interstellar visitor once its true path became clear. It has two names because it lives at the intersection of two catalogues, the traditional comet list and the short new list of bodies that come to us from other stars. It moves on a hyperbolic path that confirms it is unbound to the Sunday. It will not come anywhere near Earth and it will not come back. With that identity established, we can now ask a more detailed question. If 3I Atlas is on paper a comet from another star system, how do comets in general behave, and in what specific ways does this one depart from the patterns we know? To answer that, we have to step back from the headlines and review what a comet is, how it travels, and why some of them eventually escape the systems that form them at all. That is where we turn next. If 3I Atlas is in the simplest sense a comet from another star system, then the next step is to understand what a comet actually is. Not in the mythic sense, not as a bad omen or a cosmic sign, but as a physical object obeying the same rules of gravity, heat, and motion that everything else obeys. Once you have a clear picture of how an ordinary comet behaves, you can see more clearly which parts of 3I Atlas are familiar and which parts stand out. At its core, a comet is a small, irregular body made of a mixture of ices, dust, and rock. You can think of it as a leftover fragment from the early days of a planetary system, a piece that never grew large enough to become a planet or even a moon. In a typical system like ours, most of these fragments live far from the central star in a cold reservoir where water, carbon dioxide, carbon monoxide, methane, and other volatiles can remain frozen for billions of years. As long as a comet stays in that deep freeze, it is dark and quiet, almost indistinguishable from an asteroid. The behavior that most people associate with comets begins only when one of these bodies is disturbed. A distant gravitational nudge from a passing star, the collective pull of giant planets, or the slow evolution of orbits over time can send a comet inward toward the star. When that happens in our solar system, the comet finds itself falling along an elongated path, an ellipse that stretches from the cold outskirts to the inner regions and back again. Near the far end of the ellipse, it creeps along very slowly. Near the star, it races. This trade between speed and distance is one of the basic features of orbital motion. As the comet approaches the star, the sunlight it receives increases sharply. For a long time, nothing visible changes. The nucleus is still cold and dark, absorbing energy into its surface. Then at some distance, that depends on its composition, the top layers begin to warm enough that the ices can no longer remain solid. They pass directly from solid to gas, a process called sublimation. Gas seeps out through pores, cracks, or vents carrying dust with it. Around the nucleus, a thin, expanding atmosphere forms, which we call the coma. Under the pressure of sunlight and the flow of charged particles from the star, gas and dust are blown back, forming tails that point away from the star. This is the stage where comets become visually dramatic, but there is a quieter story underneath. Every bit of gas that escapes represents a loss of mass. Over many passages, that loss changes the nucleus. Layers peel away, cavities form and collapse. Fresh ice is exposed in some regions, while others become coated with darker, more refractory material that suppresses activity. Eventually, if the comet survives long enough, it can turn into something that looks more like a dark, inert asteroid, having shed much of its volatile content. The escaping gas also does something subtle to the comet's path. When gas jets out in one direction, it pushes the nucleus in the opposite direction. in the same way a weak rocket exhaust would. The force is tiny compared to gravity, but it acts over long time. If activity is concentrated on one side of the comet, or if certain vents flare up in a regular pattern as it spins, the accumulated effect over many orbits can shift the trajectory by a measurable amount. Astronomers call these shifts non-gravitational accelerations, and they are a normal part of comet dynamics. Gravity remains the main architect. A comet on a very elongated ellipse can be perturbed by planets as it passes through the inner system. When it comes near a giant planet like Jupiter or Saturn, the gravitational pull of that planet can bend its path, either tightening the ellipse, loosening it, or in rare cases reshaping it into an open curve. The outcome depends on details like the relative positions and speeds of the comet and the planet, much like the way a spacecraft can use a gravity assist to change its path without firing an engine. Over billions of years, scattering events like these can populate the distant reservoirs of comets and occasionally eject some of them completely. The distinction between a bound comet and an unbound one comes down to a single idea: whether the total energy of its orbit is negative or positive. You do not need equations to grasp this. If the comet is bound, it is like a ball thrown upward that slows, stops, and falls back. The path is an ellipse, and though it may take centuries or millennia, the comet will return. If the comet is unbound, it is like a ball thrown so fast that it never falls back. The path is hyperbolic, an open curve that carries it past the star once and then out to infinity. Local perturbations can flip a bound orbit to an unbound one, but only if the comet is in the right place at the right time with respect to a massive planet. In our own system, we see the whole range. There are short period comets like Halley that return every few decades. There are long period comets that come from the distant Oort cloud and take millions of years to complete an orbit. And there are a few special cases like 2I Borisov that clearly arrived already unbound, with speeds and directions that cannot be produced by any known planetary encounter within our solar system. These are the genuine interstellar visitors, and 3I Atlas is one of them. So when you and I look at 3I Atlas and call it an interstellar comet, we are not making a poetic statement. We are describing a specific type of orbit and a specific kind of behavior. Its hyperbolic path tells us that it is not gravitationally tied to the sunday. Its visible activity tells us that it contains volatile ices that respond to sunlight. The combination puts it in the comet category, just not in the familiar subclass that was born here. From a formation perspective, the natural story is straightforward. In its home system, a young star would have formed out of a cloud of gas and dust. Around it, a disk would have taken shape with temperatures dropping as you move away from the star. In the colder regions, ices could condense along with dust grains, allowing cometary nuclei to grow. Over time, as planets formed and migrated, gravity would have shuffled these small bodies around. Some would have been thrown into wide distant reservoirs, some would have been drawn inward and destroyed, some would have remained in relatively stable belt, and a tiny fraction would have been accelerated past the escape speed of the star set loose into the vacuum between systems. 3I Atlas most likely belongs to that last group. It may have spent hundreds of millions or billions of years traveling through interstellar space, its surface altered by impacts, cosmic rays, and rare encounters with other objects. Only when it came close enough to our sun did it begin to act like a comet in the way we recognize shedding gas and dust, developing a coma and creating a tail. The hyperbolic orbit we see today is simply the continuation of a long journey that began when it was pushed out of its own system. Understanding all of this gives us a baseline. Comets are not gentle, stable artifacts. They are fragile, evolving bodies whose activity can be messy and asymmetric. Their orbits can be stretched, twisted, and occasionally broken open by gravity and by their own outgassing. When you place such an object in a new stellar environment with different radiation and different geometry, you should expect surprises. That expectation does not solve every puzzle posed by 3i Atlas, but it shapes how we read those puzzles. In the chapters that follow, we can now look at its specific anomalies against this background and decide which ones truly demand new physics or new ideas, and which ones simply reflect the fact that this comet is a traveler from a place we have never sampled before. 3i Atlas follows the basic script of a comet, a nucleus that sheds volatile material as it approaches a star. But it adds enough deviations from the usual pattern that several scientists paused before treating it as just another icy visitor. These deviations do not imply technology, but they deserve careful, methodical attention. To understand why this object drew so much discussion, you and I need to look at each of its unusual characteristics with a clear, steady frame of reference. None of these features alone overturn the comet interpretation, yet together they form the list of questions that spark the entire debate. The first anomaly is its estimated scale. Interstellar objects are rare. Interstellar objects of notable mass are even rarer. Early estimates of 3i Atlas suggested a broad mass range, anywhere from the equivalent of a few dozen aircraft carriers to numbers that could rival 1 million of them. The uncertainty comes from the difficulty of distinguishing a bright coma from the nucleus inside it, especially at great distance. A large coma can make a small nucleus look bigger than it is, and a dust-rich coma can reflect more light than expected. Even with those uncertainties, the probable mass of 3i Atlas remains substantial. That matters because a natural comet can be large without issue, but a technological craft of that scale would be extraordinarily inefficient. The energy required to accelerate such a massive object across interstellar distances would be immense. If one imagines a civilization with the means to cross between stars' compact and efficient designs would make more sense than a drifting mountain of mixed chemicals. This is not a conclusion, it is simply one piece of context. The second anomaly is chemical. When the first spectroscopic readings arrived, they showed a coma unusually rich in carbon dioxide. In many comets from our own system, water vapor dominates the gas output once a comet warms enough to sublimate. Carbon monoxide and carbon dioxide are present, but typically in smaller proportions. In 3i Atlas, early measurements suggested carbon dioxide exceeding water vapor by a wide margin. Later readings added more layers, cyanide nickel atoms, and most intriguingly to some, the compound nickel tetracarbonyl. This last one drew attention because it is known on Earth primarily as a manufactured substance used in industrial metal purification. That, however, does not make it inherently artificial. Interstellar environments, distant protoplanetary disks, and cold outer regions of systems can produce complex carbon metal compounds under the right conditions. The mere fact that a molecule is rare in our region does not imply it requires a factory. The chemistry does tell us something though. 3i Atlas did not form in a region identical to the birthplace of our local comets. Its volatile mix and dust composition reflect temperatures, pressures, and material abundances that do not match our own. That is exactly what one might expect from interstellar diversity. Planetary systems form under a wide range of conditions. Some grow around metal-rich stars, others form in colder disks where water ice plays a smaller role. 3i Atlas may simply be shedding the signature of a distant system whose environmental fingerprint is different from ours. A third anomaly is activity time. Many comets in our system only become visibly active when they approach the approximate distance where sunlight has enough energy to warm water ice. That threshold sits a little beyond the orbit of Mars. 3i Atlas began to activate earlier at more than 3 astronomical units from the Sunday. Detected water signatures at that distance indicated that either the water was stored in unusually large, easily heated grains, or that other volatile compounds were driving early sublimation. As it moved inward, its output rose sharply, leading some observers to describe its activity as disproportionately strong. When a comet loses mass rapidly, the structure can weaken, leading to fractures, shedding of fragments, or in rare cases, full breakup. Reports in late October and early November suggested possible fragmentation. These changes are dramatic, but not unprecedented. Comets break, crack, and split more often than most people realize. Their construction is porous, layered, and irregular. A slight shift in thermal stress can rip them apart. The fourth anomaly concerns how 3I Atlas interacts with sunlight. Polarization studies measure how scattered light aligns in particular directions after interacting with dust. Most comets show a distinctive pattern, a small negative polarization branch at certain angles. In 3I Atlas, that dip appeared deeper and shifted compared to typical comets. This indicates that the dust grains around the nucleus likely have a different microstructure, perhaps more porous, perhaps more irregular, perhaps coated with unusual compound. Again, being different from our local comets does not imply artificiality. Dust in distant systems can aggregate under different conditions, producing grain properties that are new to us. If you and I had fragments from 10,000 other star systems, we would expect extreme variation. Finally, the orbit deserves a precise look. 3I Atlas is retrograde, meaning it moves opposite the direction of the planets. That alone is not surprising. Many comets have retrograde orbit. What made some astronomers raise their eyebrows is its alignment. Its orbital plane lies only a few degrees from the ecliptic, the broad flat plane where most planets orbit. A random interstellar object could arrive from any direction in the three-dimensional sky. Only a small percentage would happen to align near the ecliptic. So statistically, it is mildly unusual, but mildly unusual does not mean purposeful. The sky is not a uniform sphere of arrival directions. Interstellar objects carry complex histories shaped by gravitational encounters, stretching back through time. A small tilt alignment is interesting, not definitive. Put together, these anomalies paint 3I Atlas as a comet with atypical chemistry, strong early activity, unusual dust, a near ecliptic path, and a size that remains on the high end of our expectations. These features explain why some people hesitated before placing it comfortably in the natural category. But none of these features, individually or collectively, require technology as an explanation. They form a list of differences, not a list of impossibilities. The role of this chapter is not to decide what 3I Atlas is, but to describe the traits that fuel the debate. If you and I can look at those traits clearly without forcing them into any particular narrative, we can follow the evidence where it leads. The next step is to examine the strongest case offered for a technological interpretation, the arguments put forward by Avi Loeb and those who share his view. That is where we turn now. When you hear people say that 3I Atlas might be a ship, they are rarely inventing that idea from nothing. They are usually echoing or amplifying the position of one particular scientist. Avi Loeb has become one of the most visible voices, arguing that some unusual interstellar objects could be technological rather than natural. To understand why 3I Atlas was pulled into that frame, you and I need to walk through his reasoning carefully, not to agree or disagree by default, but to see how he builds his case. Loeb starts from a simple premise. Humanity now launches hardware into space. Our rockets, probes, and satellites can leave traces that would be visible to an outside observer with good instruments. If we can do that after only a brief technological history, then an older civilization might have done far more. In that light, a small fraction of the objects we see in space might not be natural debris at all, but relics or active machines. This premise is speculative, but not unreasonable. It is a way of saying that technology is one possible contributor to the population of objects moving between stars. When 3I Atlas appeared, Loeb examined its photometric profile, the way its brightness changes with time and distance. In his blog and interviews, he argued that the light might not be fully explained by sunlight reflecting off a diffuse coma and tail. Instead, he suggested that a more compact light source with a size smaller than 100 meters might be responsible for a significant fraction of the observed glow. That compact source, in his view, could be a nuclear engine or a power plant of some kind, one that produces heat or light in a way that stands out from passive reflection. This is a bold interpretation. It takes a feature that others treat as part of the dust and gas distribution and recasts it as a potential sign of machinery. Loeb then looks at the motion. Astronomers routinely model the paths of comets by combining gravity from the sun and planets with small non-gravitational terms from outgassing. In most cases, those extra terms fall within a predictable range. For 3, I-Atlas, Loeb claims that the apparent non-gravitational acceleration is stronger than expected for a natural comet at that distance and with that level of activity. He reads this as a hint that something more than random jetting of gas is at work, perhaps a controlled thrust. To him, the extra zip near perihelion is a possible clue that energy is being directed, not just vented. Trajectory geometry is another piece of his argument. When you simulate many random interstellar arrivals and let them intersect the moving orbits of planets, only a small fraction will pass close to those planets. Loeb has stated that if you vary the arrival times over a wide range, only a small subset of cases yield a path like that of 3. I-Atlas, one that passes within relatively short distances of planets like Mars or Jupiter. From this, he infers that the probability of such a close tour being purely coincidental is low. In his framing, a close planetary pass is not simply an accident. It could be a deliberate reconnaissance pattern, a way to sample several worlds in a single dive through a system. On top of these physical arguments, Loeb expresses concern about the completeness and transparency of the data record. He has spoken about images taken by the Mars Reconnaissance Orbiter during a close approach and has questioned why certain data sets have not yet been made public. This perceived delay feeds a narrative of missing information. If you already suspect an unusual origin, any gap in the data flow can look like suppression. In reality, archiving and releasing spacecraft data can be slow, but the timing still becomes part of the story he tells. A final component of his case is chemical. The detection of nickel tetracarbonyl, a compound associated on Earth with industrial metal processing, becomes, in his view, more than a curiosity. If a craft used nickel in its structure or for heat-resistant coatings, he argues some fraction could be released into the surrounding gas, creating an artificial signature. The fact that this compound is rare in our natural environment makes it tempting to treat it as a fingerprint of some engineered process, rather than an exotic but natural product of alien chemistry. Here again, the leap is speculative. The same molecule can have multiple formation paths, natural and artificial, and distinguishing them remotely is extremely difficult. When you assemble these strands, the picture Loeb draws is straightforward. 3I Atlas, in his reading, is a large structure that emits its own light from a compact region, accelerates in ways that resemble thrust rather than random jetting, follows a path that conveniently inspects multiple planets' releases, chemicals that resemble industrial byproducts, and travels through our system as though on a reconnaissance mission. In that story, it may be a mothership, it may release smaller probes, it may even be related in some indirect way to the unidentified aerial phenomena reported in our own atmosphere. None of these conclusions are demanded by the data, but they are, in his view, consistent with one possible interpretation. It is important for you and me to note two things at this point. First, Loeb does not present his view as settled fact. He calls for more observations and invites other scientists to test or refute his ideas. Second, his framing is built on stacking multiple low probability readings in the same direction. Each individual piece could have a mundane explanation, but taken together, he feels they argue for a technological origin. This is a common pattern in speculative reasoning. You gather anomalies, interpret them in a coherent way, and propose a bold hypothesis. The value of his position, even if you ultimately disagree, lies in the way it forces the community to check its assumptions. It is easy for any field to become conservative, to treat every new object as a variation on the last. By insisting that we consider artificial origins, Loeb pushes other astronomers to tighten their models, refine their measurements, and articulate clearly why a natural explanation remains sufficient. That kind of push and pull can be healthy as long as the line between data and speculation stays clear. For this narrative, the key is not to decide here whether Loeb is right or wrong. The key is to understand that his case rests on reading every unusual feature of 3I Atlas in the most dramatic possible way. It is a lens. Through that lens, the comet becomes a suspect vehicle. Without that lens, the same features can be read as signs of a messy, volatile body from a very different birthplace. In the next part of our journey, I want to show you how the broader community reads the same data with a simpler set of assumptions, and why for now the natural comet interpretation remains the one most strongly supported by the evidence. When you take the full set of observations of 3I Atlas and hand them to most astronomers, planetary scientists or dynamicists, the conclusion they reach is consistent. They do not see structured thrust. They do not see controlled motion. They do not see engineered heat sources or deliberate signaling. What they see is a volatile, active interstellar comet behaving in a way that is unusual only when compared to comets formed in our own backyard. To understand why that judgment is steady across multiple institutions, you and I need to walk through the reasoning step by step. The starting point is the coma itself. Comets in our solar system often show strong water emission only inside roughly 2.5 astronomical units. 3I Atlas began showing activity earlier, but that behavior aligns with objects that contain high proportions of carbon dioxide or carbon monoxide. These ices sublimate at lower temperatures and can drive early outgassing long before water warms to the same threshold. Observatories that track the gas chemistry, including telescopes operated by NASA ESA and ESO, saw emission lines that fit naturally with a carbon dioxide dominant coma. Water was present, but not as the main driver. This is not a sign of machinery, it is a sign of an unfamiliar composition. Interstellar objects should have unfamiliar compositions. Radio detections tell a similar story. The Meerkat Array in South Africa succeeded in detecting hydroxyl radicals in late October after 2 earlier attempts. Hydroxyl is a normal byproduct of water molecules being broken apart by sunlight. If the object had been something other than a natural comet, we would not expect to see this pattern, or at least not with the clarity observed. The presence of hydroxyl is a simple physical indicator that water ice is sublimating in real time as the object approaches the sunday. It does not answer every question, but it anchors the interpretation firmly on natural ground. The non-gravitational acceleration, which some viewed as an artificial thrust, fits comfortably within comet physics as well. When a comet emits gas asymmetrically, the reaction force changes its motion slightly. These small pushes are visible in many comets and are modeled using standard terms that describe how outgassing varies with distance from the sunday. For 3I Atlas, the measured deviations are on the strong side, but they remain within plausible ranges when you consider its unusual chemistry and high carbon dioxide content. A carbon dioxide-rich comet can experience larger than usual reaction forces because carbon dioxide throws off more momentum per molecule than water vapor. This is routine physics, not evidence of controlled propulsion. Brightness variations, another pillar of the artificial hypothesis, also look normal when interpreted through the lens of comet behavior. Comets develop dust jets, rotating fans, and temporary bright patches as they spin. Observers on Earth see these variations as changes in brightness, sometimes smooth, sometimes irregular. 3I Atlas shows the same kind of variability, modulated by its spin, by its internal structure, and by the constantly changing release of ices. When people say the coma looked like jets, they are not wrong, but jets are standard cometary features. A jet is simply a concentrated vent of gas and dust. It is not a thruster unless its timing, direction, and energy output suggest deliberate control. No such pattern has been detected. The unusual dust properties also fall within the range of natural expectations. Polarization studies showed a deeper than usual negative branch at small phase angles and a delayed flip to positive polarization. That indicates that the dust is likely more porous or more irregular than typical comet dust. But dust grains form under a wide range of conditions. Interstellar dust environments can differ drastically from ours. A variation in dust microstructure is not a sign of engineering. It is a sign of diversity in planetary system formation. Then there is the problem of technosignatures. If a structure the size of Manhattan were technological, you would expect more than one anomaly. You would expect waste heat detectable in the infrared. You would expect structured radar reflections. You would expect narrow radio emissions or modulated light patterns. You might expect changes in trajectory that follow clean directional pulses rather than irregular vents. Multiple teams searched for such evidence. NASA's Deep Space Network looked for radio emissions. Optical surveys searched for photometric modulation that might suggest rotation of a rigid structure. Infrared instruments searched for thermal signatures inconsistent with sublimation. Every one of those searches returned null results. There was no heat pattern that resembled a reactor. There was no sign of internal illumination. There was no coherent transmission at radio wavelength. The object behaved like a natural body interacting with sunlight, not a machine producing energy. Size is another sticking point. The speculative scenario imagines a technological object, hundreds of billions of tons in mass. Accelerating such a mass across interstellar distances would be an extraordinary waste of energy, even for a civilization far beyond our level. Every real probe we have built shares a common trait. It is as light as possible. Even when we build heavy craft, like the Cassini or Galileo probes, their masses are measured in tons, not megatons. And if you wanted to disguise a probe as a comet, you would not select a gigantic nucleus that draws attention by shedding enormous volumes of gas. You would choose something compact, stable, and subtle. 3I Atlas is none of these things. Its mass estimates, even at the low end, place it many orders of magnitude above any reasonable robotic design. The orbital alignment also becomes less suspicious when viewed through the correct statistical frame. The solar system is not a uniform target session. The ecliptic is dense with mass. Objects that pass near massive regions are more likely to be perturbed into shallowly inclined paths over billions of years. The fact that 3I Atlas approaches within a few degrees of the ecliptic is interesting, but it is not smoking gun. Retrograde comets also exist in large numbers within our own system. The combination is uncommon, but not outside the expected range of random interstellar arrivals. This broader view does not reject curiosity. It does not dismiss the possibility that someday a technological artifact could enter our system. What it does is apply a standard method. When natural explanations are sufficient, they are preferred. 3I Atlas displays chemical, physical, and dynamical features that all fall within the space of cometary behavior when you consider that it comes from a completely different system with different formation conditions. None of the features require engineering, none demand intelligence, none violate physics as we know it. The mainstream scientific interpretation settles here. 3I Atlas is unusual because it is interstellar. Unusual chemistry, unusual dust, and unusual timing are expected when you sample an object formed under conditions we have never catalogued. The object is not quiet or stable because interstellar comets are not required to resemble our local templates. They are travelers shaped by environments far from anything we have measured direct. Now that the natural interpretation is clear, you and I can move to a more imaginative question. If someone truly wanted to turn a comet into a starship, how would they do it? And how closely would such a craft resemble 3I Atlas? That is where our next chapter leads. If you imagine crossing the distance between stars using technology that is only a few steps beyond what we have today, a comet starts to look like a tempting piece of hardware. It is already a shield, already a fuel tank, already a warehouse of carbon, oxygen, nitrogen, and metals. Even if 3I Atlas is natural, you and I can still use it as a mental model for what a comet starship might look like in physics, not in fiction. When we do that carefully, we can see both how the idea could work and why 3I Atlas does not resemble a practical implementation. Start with the advantages. A comet nucleus offers mass and protection. Interstellar space is filled with high-energy radiation and fast particles that can damage electronics and biology. A thick shell of rock and ice provides excellent shielding. If you hollow out internal chambers inside a comet, you can build habitats buried under tens of meters of material, safe from the worst of the radiation. That is better than trying to carry an artificial shield from scratch. The mass is already there. The second advantage is resource density. Comets contain water, ice, carbon dioxide, ice, various organic compounds, and silicate dust. Water can be broken into hydrogen and oxygen for breathing and for fuel. Carbon compounds can feed life support systems or serve as propellant. Metals can be refined for repairs and manufacturing. In principle, a single large comet could support a closed ecosystem and a propulsion system for long periods. It is a combined tanker and construction yard. The third advantage is dynamical flexibility. A comet starship could use the same gravity assist tricks that we already apply to our vessel. By diving near a star, the craft could use the O-berth effect, firing its engines when it moves fastest to extract more benefit from each unit of propellant energy. The same principle applies around giant planets. A careful sequence of dives and burns could take a comet-based ship onto a trajectory that leaves its home system and heads toward another star. None of this requires new laws of physics. It only requires patient engineering and careful navigation. With those advantages in mind, picture the actual process of turning a raw comet into a vessel. First, an engineering civilization would identify a suitable nucleus, large enough to provide shielding and resources, small enough that its mass does not become a crippling burden. Then they would stabilize its spin shore up weak regions and probably remove fragile outer layers to reduce the risk of spontaneous breakup. Inside, they would excavate cavities, install structural supports, and lay out living and working spaces. They would also embed power systems, nuclear reactors, or advanced solar systems to power life support, propulsion, and control. For propulsion, they could use the comet's own volatiles. By heating selected regions and venting gases through nozzles, they could turn natural sublimation into directed thrust. In that sense, the boundary between a natural jet and an engineered exhaust is thin. The difference is control. In a ship, timing direction and thrust levels would follow an intentional pattern. The engines would fire in clean sequences, matching precise changes in trajectory. Waste would be minimized. Random vents would be suppressed or sealed. The crew would not permit valuable mass to leak in unpredictable directions. If stealth were a goal, there are two main options. One is to stay quiet, minimize activity, reduce thermal signatures, and avoid bright flares. A cold, inert chunk of material is hard to distinguish from a natural rock. The other option is to mimic a comet so accurately that any observer catalogues it as just another volatile, rich body. This second path is complicated. To mimic a comet convincingly, the ship would need to reproduce the same relationships between gas output, dust composition, and orbital position that natural comets show. It would also have to respect the constraints of fuel economy. There is no reason to burn propellant in extravagant ways simply to look messy. Now compare this picture to 3I Atlas as we observe it. 3I Atlas sheds mass early and uncontrollably. Its activity began far out, and the gas output increased dramatically as it approached the Sunday. There is no sign that the outgassing is focused into a small set of repeatable efficient exhausts. Instead, the coma shows complex chaotic structures. The jets appear in multiple directions. The brightness changes are irregular. From a propulsive standpoint, this is an extremely wasteful way to travel. If someone spent enormous energy to accelerate a body of this mass through interstellar space, they would not casually throw away large fractions of it in an uncontrolled boil. Sizing is another mismatch. A practical comet starship designed by engineers concerned with energy would likely use the minimum mass necessary to meet its shielding and life support needs. Think of a thick shell, not a continent. 3I Atlas may sit at the high end of the mass range for comet nuclei. Moving such a body across interstellar distances at significant fractions of light speed would require energies in line with large fractions of a star's output over long periods. Even at modest speeds, the cost is enormous. A civilization could choose to accept that cost, but efficiency tends to push designs towards smaller carriers, perhaps fleets of compact ships, rather than one colossal hull. Trajectory control also looks wrong for a ship. If you study the path of 3I Atlas, you see a mostly smooth, hyperbolic orbit determined by gravity. There are small deviations due to outgassing, but no evidence for sharp course corrections or complex maneuvers near planet. A careful navigator using a comet shell as a vehicle would exploit planetary encounters more aggressively. For example, they might tune the timing so that the craft swings close to Jupiter to gain or shed velocity in a precise way. They might adjust the perihelion distance to maximize or minimize solar heating. 3I Atlas does none of these things. Its flybys are distant, its perihelion is modest, it follows a clean natural arc. Signal management is yet another point of divergence. A real ship needs communication channels, internal and external. Those channels would likely generate detectable radio emissions, narrowband lasers, or at least structured thermal pattern. Advanced civilizations might develop ways to hide these outputs, but the burden of proof then shifts entirely to invisibility. 3I Atlas has been observed across multiple wavelengths. In every band, its behavior matches expectations for a natural cometary body sunlight reflection in the optical gas emission lines in the radio thermal emission consistent with solar heating. There is no obvious excess, no regular modulation, no beacon-like feature. All of this leads to a simple statement: comet starships are physically possible in principle. If a civilization wanted to build long-duration habitats within cometary shells, use volatile ices as propellant and ride gravity assists out of their system physics would allow it. You would not need exotic drives or faster than light tricks. You would only need robust engineering patience and the willingness to accept that journeys might last many generations. Under those conditions, yes is a reasonable answer to the question of whether comet ships could exist someday. But when you and I turn that answer onto 3I Atlas, it becomes yes-ish at best. The object we see in our telescopes does not behave like a vehicle built by engineers concerned with efficiency control and survivability. It expends mass in uncontrolled ways. It shows no deliberate course shaping, it exhibits no unambiguous technosignatures. It looks in every measurable respect like what you would expect from a large volatile comet, whose ingredients and structure are tuned by an alien birthplace rather than alien intention. This distinction matters because it keeps our imagination grounded. Exploring comet ships as a thought experiment helps us understand what signs we might look for in the future. We can ask what a controlled exhaust pattern would look like, how a disguised ship might manage its thermal output, how its orbit might differ from a purely natural path, and what kind of chemical signatures its operation would leave behind. Those questions are useful. They sharpen our search criteria. They make us better prepared for the day when an object truly does defy all natural explanation. For 3I Atlas, however, the conclusion remains straightforward. The idea of a comet starship gives us a language to talk about the possibilities, but it does not apply well to the object we are currently watching. 3I Atlas is almost certainly not a ship. It is a natural body whose behavior is unusual only because our experience with interstellar materials is minimal. That leaves us with another question, one that is less about the object and more about us. Why, given a natural explanation, are we so quick to reach for an artificial one? That is the question we will approach next. By the time an object like 3I Atlas appears in the news, most people are not starting from physics. They are starting from a feeling. A dim red interstellar body arrives from the direction of Sagittarius, changes Brightness shifts, color sheds, unfamiliar gases, and refuses to fit comfortably into the picture of normal comet that they carry in their heads. Faced with that, the fastest path your brain can take is simple. If it is strange and far away, it must be someone else's work. You see this pattern with almost every odd phenomenon that reaches public attention. The details change, but the reaction is the same. A few uncertainties are enough to awaken the word alien. There is a long history behind this reflex. For centuries, when people did not understand lightning or comets or epidemics, they connected them to gods, curses, or omen. Philosophers call this habit God of the gaps. The gaps are the parts of reality where our explanations fail. Instead of leaving those gaps open and uncomfortable, we filled them with a powerful agent. That agent could choose, decide, punish, warn. It made randomness feel meaningful. In the modern world, fewer people reach first for a deity, but the pattern of thinking remains. Neil deGrasse Tyson has talked about this in a very clear way. He suggests that in an age when we talk less about gods, aliens take over the same mental role. When someone sees lights in the sky moving in ways they do not recognize, the thought process is almost instant. I do not know what that is. Then it moves in a way I do not understand. Then, therefore, it is a ship or a craft. The leap from ignorance to agency is the same as before, just with a new label. Tyson calls this aliens of our ignorance, and 3I Atlas is a current example of how fast that label can spread. Part of the explanation lies in our impatience with uncertainty. Admitting we do not know yet is emotionally unsatisfying. It feels like a pause rather than a conclusion. A technological story, by contrast, is complete. If you say, this is a reconnaissance craft passing through our system, you have provided an agent, a motive, a mission. Every anomaly in the data can be wrapped inside that story as deliberate design. Unusual gas output becomes engine exhaust, early activity becomes a power-up phase, and near pass by a planet becomes a purposeful flyby. The narrative does not need to wait for measurements to catch up. Social media amplifies this. Platforms are tuned to reward content that triggers strong reaction. A calm description of carbon dioxide sublimation will not travel far. A short video suggesting that scientists think it might be a ship will. Once that seed is planted, repetition takes over. Algorithms push the dramatic claim to more people. Comment sections fill with speculation. Each person who hears the idea tends to share it with a slight increase in confidence, as if the very fact that it is circulating were proof of its plausibility. There is also the attraction of simplicity. A natural explanation for 3I Atlas has to deal with several layers at once. How interstellar comets form, why their chemistry may differ from local comets, how outgassing behaves under varying temperatures, how dust grain structures affect polarization, how orbital statistics work in 3 dimensions over long timescales. That is a complex stack of ideas. The alien explanation compresses all of that into one sentence. It does not act like our comets because it is not a comet. For a brain that prefers quick closure, the compressed story wins. Another ingredient is something like tribal instinct extended into space. Tyson jokes about solar system tribalism, but there is a serious core to that phrase. Humans tend to mark boundaries between us and them, between familiar and foreign. In that frame, anything born in our system orbiting our sun feels like us. Anything entering from outside becomes them. The labels alien and intruder come almost automatically. Instead of seeing 3I Atlas as a piece of natural geology shaped by an ordinary star that happens not to be ours, many people see it as a representative of a fundamentally different category, closer to a stranger at the door than a rock in a new place. Fiction feeds into this too. For decades, our films and novels have portrayed alien craft as silent, enigmatic objects that drift into a system, hover at a distance, and observe. They are rarely obvious machines. They often masquerade as natural phenomena or dark shapes. So when reality offers up an object that behaves oddly, then leaves it fits neatly into that template. The stories we tell ourselves ahead of time prepare slots in our minds. 3I Atlas drops conveniently into one of those slots. There is also a rational fear hiding inside the irrational noise, the fear of overlooking real evidence. If one day a genuine technological artifact passes through our system and we dismiss it as just another comet, that would feel like a missed opportunity on a civilizational scale. To avoid that, some people prefer to assume the extraordinary and be corrected later, rather than assume the ordinary and risk blindness. You can hear this in the way some commentators talk about 3I Atlas. They say, in effect, we should not trust experts who call it a rock because we ourselves make machines and others might too. That concern is valid in a narrow sense. We do need to stay open to the possibility of discovering non-human technology. The mistake comes when openness turns into an untested default. If every unexplained detail is treated as strong evidence of agency, the word alien loses meaning. It becomes a placeholder for "I do not recognize this pattern yet." That is not a discovery, it is a storm. So when 3I Atlas shows high carbon dioxide levels, unusual polarization and strong early activity, a scientific mindset says, we have just learned that some star systems produce comets with different volatile balances and dust structures. It does not need to say some engineer chose those properties. The data may eventually reveal processes we did not anticipate, but those processes can still be natural. Interstellar chemistry and dynamics are rich enough to surprise us without help. You and I live in a culture saturated with images of alien contact. There is nothing wrong with enjoying those stories. The key, when a real object like 3I Atlas appears, is to notice when those stories are doing the thinking for us. When you hear yourself or others say, "I cannot explain this, therefore aliens," it is worth pausing. That therefore hides the entire problem. Not knowing is an invitation to investigate, not a license to declare. In that sense, 3I Atlas is useful beyond its physical presence. It is a mirror. It shows us how quickly a rare object can be turned into a canvas for our hopes and fears. It shows how hard it is, for we do not know yet, to compete with it is a ship. And it reminds us that the most honest position when facing a phenomenon at the edge of our understanding is a combination of curiosity and restraint. We can hold open the possibility of intelligence elsewhere without assigning it responsibility for every anomaly. By now, you and I have spent a lot of time asking what 3I Atlas is not. It is almost certainly not a starship. It does not behave like a controlled probe. It does not carry the technosignatures we would expect from engineered hardware. But if we stop the story there, we miss what might be the most important part. Even as a fully natural object, 3I Atlas is one of the most valuable scientific opportunities our generation has seen. The reason is simple. It brings us a direct sample of material from another planetary system without our having to go anywhere. Think about what it takes to study a distant star system normally. We point telescopes at faint specks of light and infer their properties from tiny shifts in subtle color change. When we detect an exoplanet, we usually see only indirect fingerprints, the dimming of a star as the planet passes in front, the wobble of the star as the planet tugs on it, or a faint spectrum from a thin atmosphere wrapped around a dark globe. From those traces, we try to reconstruct atmospheres, temperatures, chemistry, and structure. It is like trying to understand an entire city from the sound of its traffic heard through a wall. An interstellar comet changes that relationship. Instead of us stretching our instruments toward another system, a piece of that system comes to us. 3I Atlas is not a theory or a light curve. It is solid matter from somewhere else, now close enough to resolve, dissect, and measure across multiple wavelengths. Even if we never physically sample it with a spacecraft, every photon we collect from its coma and tail carries information about its composition, structure, and history. Start with the chemistry. Spectroscopy lets us identify which gases and ions are present in the coma. In 3I Atlas, we see a dominance of carbon dioxide over water-strong cyanide emission and traces of nickel-bearing compound. That balance is very different from typical comets in our own system, where water usually takes the lead once sublimation begins. From this alone, we learn that some planet-forming disks produce icy bodies with different volatile inventory. Perhaps the region where 3I Atlas formed was colder or richer in carbon relative to oxygen. Perhaps its star had a different metallicity, shifting the chemistry of the disk. Whatever the exact cause, the point is clear. Our solar system is not a perfect template for all others. The dust around 3I Atlas carries a different set of clues. Light scattered by dust grains reveals their size, shape, and internal structure. Polarization measurements suggest that these grains are more porous or irregular than the dust around many local comets. That tells us something about the aggregation process in its home system. In some environments, grains may stick together gently, forming fluffy, low-density structures. In others, they may collide at higher speeds, producing compact glassy particles. The properties of dust influence how planets accrete, how heat flows through forming bodies, and how volatile ices are stored or released. By studying the scattering behavior of 3I Atlas, we are effectively reading a small part of the assembly instructions for its birth system. Even the timing and intensity of its outgassing offer insight. The fact that 3I Atlas became active beyond the traditional water frost line suggests that some comets in other systems carry ices that respond to lower levels of sunlight. This has implications for where, in a disk, planetesimals can become volatile rich, how early they start losing material, and how stable they remain over long times. In a broader sense, it informs models of how water and other volatiles might be delivered to rocky planets in those systems. Our own story of habitability depends heavily on comet and asteroid impacts. Understanding how that story might play out elsewhere requires exactly this kind of comparative data. From a dynamical perspective, 3I Atlas also helps us map the invisible population of interstellar debris. Every confirmed interstellar object gives us one more data point on how frequently stars eject material and how that material moves through the galaxy. If such visitors are common, then the spaces between systems are not empty. They are threaded with slow, sparse streams of comets and asteroids exchanging material on million-year timescale. Over the history of the Milky Way, this kind of exchange could mix organic ices and minerals between distant systems. 3I Atlas is one sample from that hidden traffic. There is a practical dimension to all of this. As we learn more about interstellar comets, we can start designing missions that do more than observe from afar. It is not unreasonable to imagine in a few decades a spacecraft capable of intercepting such an object, taking in situ measurements, or even returning microscopic samples. That would be a monumental leap-direct laboratory analysis of material that formed under a different star. 3I Atlas arrives too early for that level of response, but it helps us sketch the requirements. We can estimate typical speeds, approach geometries, and activity levels. We can refine warning systems so that future interstellar visitors are recognized and targeted quickly enough to mount an interception. There is also the philosophical value. 3I Atlas reminds us that planetary systems do not exist in isolation. During their birth and evolution, they throw fragments away. Those fragments wander for ages, occasionally cutting across orbits like ours. A comet passing through our sky is not just a visitor, it is a physical connection between stellar neighborhoods. If you and I could trace its path backward for billions of years, we might find that it was once part of a disk around a star that has long since moved far from its birthplace or even ended its life. In that sense, 3I Atlas is not just chemistry and dust, it is a time capsule. Even the debate around its nature has value. The arguments about ships and probes forced astronomers to test their models, double-check their assumptions, and refine their instruments. They pushed radio astronomers to attempt detections at the sensitivity limit. They motivated dynamicists to re-examine non-gravitational acceleration models for unusual compositions. They encouraged observers across the world to coordinate campaigns and share data quickly. The end result is a more complete picture of 3I Atlas than we might have gathered if no one had ever whispered the word alien. For you personally, as someone listening to this story, the lesson is that the universe can be exciting without violating its own rules. a natural comet from another star can be as conceptually rich as any imagined vessel. It forces us to expand our models, update our expectations, and accept that our sample of planetary architectures is still tiny. The more of these objects we study, the more we will understand how common water-rich comets are, how often carbon dominates, how dust structures vary, and how frequently systems throw their small bodies into the dark between stars. So, even if 3I Atlas turns out to be nothing more than ice rock, dust and gas, its passing matters, it adds one point to a map of galactic geology we have only just begun to draw. It sharpens questions about how other systems form planets, deliver volatiles, and sculpt small bodies. And it sets the stage for future missions that might one day chase these interstellar messengers directly. On the physical side, it will have flown past the sun, shed a vast amount of gas and dust, and then faded back into the darkness between the stars. On the mental side, it will have forced us to rehearse how we respond to the unknown. It has been a test not only of telescopes and models, but of patience, imagination, and discipline. First, it is worth stating the scientific conclusion clearly. With the data we have now, 3I Atlas is best understood as a natural interstellar comet. Its hyperbolic trajectory shows that it is not gravitationally bound to the Sun and did not gain that path from any encounter with our planets. Its activity follows the pattern of volatile sublimation under solar heating. Its gases and dust, though unusual compared with local comets, sit comfortably within the range of plausible chemistry for bodies formed in colder carbon-rich regions of other systems. Its non-gravitational accelerations match what you would expect from strong, uneven outgassing. The anomalies that drew so much attention, the early activation, beyond the usual water frost line, the dominance of carbon dioxide, the presence of cyanide and nickel compounds, the peculiar polarization, signature, the possible fragmentation, near perihelion, are exactly the sorts of differences you should expect when sampling material from a system that did not share the same birth environment as ours. If every interstellar comet looked like a twin of our local objects, that would be stranger than anything we have seen in 3I Atlas. That does not mean the story is closed. There are still questions about its exact volatile inventory, the structure of its nucleus, the details of its dust grains, and the precise way it lost mass near perihelion. Those open questions are normal. No single object reveals itself completely through remote observation. What matters is that nothing we have seen so far requires us to reach beyond natural explanations. The idea of a probe or a ship remains a speculative overlay, not a demand imposed by the evidence. The more interesting part, in a way, is what this episode says about how you and I and our wider culture handle uncertainty. 3I Atlas moved through several layers of interpretation. At discovery, it was a faint point of light with a preliminary orbit. Then it became a comet with a hyperbolic path. Then it became an interstellar visitor. Then in some corners of discussion, it became a suspect vehicle. Each step added a layer of narrative on top of a core of measurements. The people pointing telescopes at it had to work with probabilities. They could not afford to cling to the most exciting possibility. They had to weigh each observation, update their models, and adjust their conclusions. For them, the discipline is simple in concept, difficult in practice. Start with the least complex explanation that fits all the data. If that explanation breaks under new evidence, move to the next one. Do not jump ahead of what you can support. Outside professional circles, the incentives are reversed. A measured statement like this object shows uncommon chemistry that may teach us about planet formation in other systems does not spread far. A suggestion that it might be a nuclear-driven craft travels much further. So public conversation tends to tilt toward theories that feel bold even when they rest on stacked assumptions. The episode around 3I Atlas therefore highlights a gap between how science is practiced and how it is often perceived. For you as a listener, there is an opportunity here. You can train yourself to notice the difference between this is unexplained and this is evidence for design. You can pay attention to the words people use. Phrases like could be, might indicate or is consistent with belong to a very different category than shows proof of. When you see an extraordinary claim, it is worth asking what would have to be true for that claim to be the best explanation, and whether the data really push us that far. At the same time, it would be a mistake to respond by shutting down imagination entirely. The search for life and intelligence beyond Earth is a serious field. Radio telescopes scan for signals. Optical surveys look for unusual light sources. Infrared observatories watch for waste heat that might betray large engineered structures. The idea that we might one day detect a genuine artifact is not science fiction. It is a legitimate possibility. What 3i Atlas teaches is not that such discoveries are impossible, but that they require robust converging lines of evidence, not just odd behavior. There is a productive way to use imagination in this context. Instead of assigning every anomaly to aliens, we can use thought experiments about alien technology to sharpen our detection strategy. When we asked what a comet starship would likely look like, we were not trying to retrofit that picture onto 3i Atlas. We were building a template. From that exercise, we came away with concrete expectations, repeated controlled thrust signatures, rather than irregular jets mass, budgets that favor compact designs, thermal patterns that signal concentrated power sources, communication, channels that leak structured signals. Those expectations can feed into real searches independent of this specific object. 3i Atlas also gives us a sense of scale. Interstellar comets remind us that our solar system is not sealed. Material flows between systems, slowly, quietly, over vast time. Fragments of other worlds may have passed through our neighborhood long before we had instruments to notice them. Some may even have collided with planets or moons, leaving microscopic traces in rock. Seen this way, the galaxy is not a set of isolated islands. It is an archipelago connected by the drifting debris of star formation and planetary dynamic. There is a kind of humility in that view. Our sun is one star among many. Our comets are one population among many. 3i Atlas is a single piece of evidence that the processes we observe here are part of a larger pattern. In one sense, that makes us less special. In another sense, it enlarges our story. We are not confined to the materials of our own system. We live in a galaxy where matter mixed by gravity and time passes through different stellar neighborhoods carrying information in its composition. When I think about 3i Atlas leaving, I do not picture a ship fading into the dark. I picture a fragment of a distant system completing one more arc in a long, slow path that began billions of years ago. We saw it for a brief moment, asked hard questions about what it was projected our fears and hopes onto it, and then slowly refined our view back to something that fits the evidence. That sequence is not a failure. It is exactly how understanding grows. When I follow the last measurements of 3i Atlas, what stays with me is not the drama of speculation, but the steadiness of the evidence. A fragment from another star system passed through ours, behaved in ways that were unfamiliar, but still natural, and then continued its long journey out. You and I were here at the moment it arrived, which is a small coincidence in cosmic terms, yet enough to remind us how open the universe still is. The debates that surrounded it will fade, but the data will remain, and so will the questions that data open. We now know a little more about how other systems store their ices, bind their dust, and assemble their small bodies. We also know a little more about our own instincts, how quickly we reach for extraordinary explanations, how strongly uncertainty invites imagination, and how important it is to slow down until the evidence settles into something coherent. If there is something I hope you carry forward, it is the ability to hold two things at once, a curiosity large enough to welcome the unexpected, and a discipline strong enough to wait for measurements before drawing conclusions. That balance is what allows science to expand its reach without losing its grounding. As the object fades into distance, I think of it as a reminder that the universe does not need to be artificial to be astonishing. Sometimes a natural comet arriving at the right moment is enough to widen the boundaries of what you and I can imagine.